Well, the last video you watched on applying Kirchhoff's rules might have come at you a little fast or been a bit confusing. You probably need to do a few examples of applying Kirchhoff's rules for non-reducible circuits until you become familiar with it. Maybe in particular, expressing the equations in the form of a matrix. So you should recognize this first question. That's the one from our last lesson. We had identified two junctions, and we guessed that there's a current we call I1 flowing upward through the 8-volt battery. We also guessed that there's a current that we labeled as I2 flowing upward through the 12-volt battery, and we guessed that there was a current flowing downward through the 5-volt battery that we called I3. In the end, I3 was equal to 3.5 amps, I2 is equal to 2 amps, and I1 is equal to 1.5 amps. Any question you can be asked from there, maybe what's the voltage across a given resistor, or what's the power consumption for a given resistor. That all becomes easy as long as you have our two basic equations. Voltage across any circuit element is equal to the current through it multiplied by the resistance, or I should say the voltage across a resistor is given by this equation, and the power consumption of a resistor is the value of current squared multiplied by resistance. So as long as you know the current, you can solve for voltages and power values as well. Well, I'll leave it up to you if you want to do this problem number 2. So if you need to hit pause right now and copy that picture and try the same 4-step approach. Step 1, identify the junctions. Step 2, guess the currents. Step 3, apply the junction rule. And step 4, apply the loop rule. Okay, we're going to do problem number 3 together in this video lesson. The question is, what amount of energy is dissipated by the 3-ohm resistor if the circuit's been connected for 20 minutes? Well, let's see. Gosh, I know I could find power through the 3-ohm resistor by multiplying the current squared times its resistance, but what about energy? Well, power is also energy divided by time. So in other words, energy is equal to power times time. So the energy would be the current squared times the resistance times the time. We could think of 20 minutes as being 1,200 seconds. So we know what value of time we'll be using. We know what value of resistance we'll be using. 3 ohms, 1,200 seconds. The question is, what the heck is the current? Well, the way we figure that out is by applying these 4 steps. Identify the junctions, guess the currents, apply the junction rule, and apply the loop rule. So we can draw the picture a little bit bigger and work off of that diagram. By the way, if you go into the shared folder for this class, you'll find there's a file called Circuit Solver, and it's an Excel file. It's a spreadsheet. You can use that file to plug in values, and it's kind of like a program then that'll just spit out the correct answers. So probably not a good idea to use that to answer the questions on your homework. Better you work it out on paper to answer the questions and then you can use the circuit solver just to check to see if you got it right. So here's the problem. We've got to figure out how much energy in 20 minutes for this circled resistor. Let's start by identifying the junctions. Clearly, there are only 2 junctions in this circuit. We'll label them as A and B. And now we're going to guess the currents. Okay, I'm going to guess that there's a current flowing into junction A through the 16-volt battery, and I'll call that I1. Then I'm going to guess that there's a current going this way from A to B across the 10-volt battery. We can call that I2. And then there's a current also going from A to B through the 4 ohm resistor and the 2 ohm resistor. We'll call this one I3. So if I want to apply Kirchhoff's junction rule, I can apply it to junction A and say I1 flows in, I2 and I3 flow out. Now I can rewrite that as I1 minus I2 minus I3 equals 0. Let's apply the loop rule. How about I use this upper loop? Okay, and I'm going to start at point B. How's that? And I'm going to come back to point B, and I'll trace my way around, how about in a clockwise direction. So the first thing I encounter is the 10-volt battery. So plus 10. Now as I work my way around, the next thing I'll encounter is this 4 ohm resistor. Now I'm tracing my way across that resistor in the direction of this current labeled as I3. So that means it's a voltage loss. So this is minus 4 I3. The next thing I encounter is this 4-volt battery. That's going to be a gain in voltage going from negative to positive. And then I'm encountering the 2 ohm resistor in the direction of the current I3. And I'm back to point B, so I can say this is all equal to 0. Of course, I can rewrite this in the form 0I1 plus 0I2 minus 6I3 is equal to negative 14. And how about I get my last loop by working my way around the lower loop, and again I'll start at point B and I'll go in a clockwise direction to come back to point B. So the first thing I encounter is this 3 ohm resistor in the direction of the current. Okay, so I have minus 3, and which current is that? That's the current I1. So minus 3I1 plus 16 volts minus 1 I1 minus 10 volts. Right? That's the last thing I'll encounter, is going from the positive to the negative across that battery. And that brings me back to point B, so that equals 0. Of course, I can rewrite this and put this in the form negative 4I1 plus 0I2 plus 0I3 is equal to negative 6. If I rewrite all three of these equations in matrix form, I get 1, negative 1, negative 1, 0, 0, 0, negative 6, negative 14, negative 4, 0, 0, negative 6. Of course, I really don't have to go through this whole row reduction process. Remember, what any one of these rows is a standalone equation, and if I have two zeros in that row, then I'm just saying that negative 4I1 is equal to negative 6, multiply both sides by negative 1, I1 is equal to 6/4, which is 1.5 amps. If I look at row number 2, this just tells me that negative 6I3 is equal to negative 14, multiply both sides by negative 1, I3 is equal to 14/6, and we'll just call that 7/3 of an amp and leave it at that. And then we get I1, minus I2 minus I3 is equal to 0. So we have 1.5 amps minus I2 minus 7/3 of an amp is equal to 0. So I2 is 1.5 amps minus 7/3 of an amp. Let's see, 7/3 is the same thing as 2.33. Oh, wait a minute. This means I2 is negative 0.83333. Ooh, I2 came out negative. Shh, don't tell anybody. Now that I'm done solving for all of my currents, we'll keep this our little secret. I'm just going to fix this I2 right here and change the direction of the arrow this way. And then I'll say, just kidding, it's really positive 0.833. So there we have it. I know all of my currents. I1 is 1.5 amps. I2 is 0.83 repeating amps. And I3 is equal to 2.3 repeating. If I want to find how much energy is consumed by the 3 ohm resistor in 20 minutes, I just need to multiply the current I1 squared times 3 ohms times 1,200 seconds to give 8,100 joules. Okay, that actually turned out to be easy. Solving this matrix didn't really require any row reduction at all. That won't always be the case. The reason that happened for this circuit is kind of basic, because there was no resistor on this path where the current I2 is flowing. And so our mathematical statements didn't have two different currents, or two different currents in any one equation. So that became pretty straightforward. I think you'll find, if you attempt to do question number 2, that you will have to apply some row reduction for the matrix that you have to solve. In the end, don't forget, you can use the circuit solver to check your answers. Or, of course, if we have any live meetings, you're always welcome to ask your professor. All right. As always, thanks for watching.